Section 3.10, linear approximations and differentials. So there's two parts to this section, and which really, the two topics themselves in terms of the calculations that are going to be done and the processes, there's really nothing new here. What's going to be different is some of the language, some of the notation that we use or talk about. So for that reason, obviously, it could be a little bit confusing, but the first part of it where we talk about linear approximations, ultimately that is nothing more than finding the equation of a tan line, which we've already done. We're just going to use a little bit of different language and notation to describe how we're going to be using it, right? So more so than just saying find the equation of a tan line, let's actually use it to approximate a curve. Right? So that's why we call it a linear approximation. The second part of this, the differential, is going to require nothing more than finding a derivative. Right? And so there's nothing new there, but the difference is going to be what we mean by dy and dx. So when we find our derivative dy dx, what does dy actually tell us? What does dx actually tell us with respect to a particular function? Okay, so it's going to be a little bit more specific in that sense, right? But again, process-wise, there's really nothing new here. So just watch the language, watch the terminology, watch the notation, as always. So that's always the thing we harp on. All right, so let's start with the linear approximations. All right, so we can use a tan line at a point, say AF of A. All right, so I'm picking a specific point. We can use the tan line as an approximation to the curve y equals f of x, as long as our x value is near the a value, right? And so this kind of goes back to our original discussion of the tan line. And actually when we started with the secant line, right? And we used the secant line, we picked 2 points on the curve and we moved 1 point closer and closer to the other point. And we said as the points get closer together, the slope of the secant line was a better and better approximation to the slope of the tan line. So what we're after in this case is actually then using that tan line as the approximation to our curve, but we have to be relatively close to that specified a value, for the same reason, because the further away we are from the actual point in question, then we lose the accuracy of our approximation. So we still need x to be relatively close to a. All right, so that's the general idea. So let's go with notation first of all and some language. So from our equation that we've used before to write the equation of the tan line, that's one of the reasons I prefer this equation, so that y minus y1 equals m times x minus x1, that point slope formula. The equation of the tan line at the point where x equals a, so at the point a, f of a, can be equivalently written as, instead of x1 and y1, I'm using a and f of a as the coordinates of our point. So here's our y minus the y coordinate of our point, x minus the x coordinate of our point, which is a, and then we have our derivative, or the slope of our tan line, which is our derivative, right, which is f prime at a. So y minus y1 m times x minus x1 equivalently is y minus f of a equals f prime at a times x minus a. Same equation, just different notation. And then I took that equation and solved it for y, so I just rewrote it as y equals f of a plus f prime of a times x minus a. Same equation, just rewritten. So we could say then that the function f of x, right, so just replacing y with f of x, can be equivalently written as f of a plus f prime of a times x minus a, which is called the linear approximation, or the tan line approximation, of our function at a. All right, so again, all that is nothing more than the equation of your tan line, just rewritten, different notation. That's all it is. Now, splitting hairs a little bit, so we call that the linear approximation, or the tan line approximation to our curve, this f of a plus f prime of a times x minus a. the function whose graph is the tan line, we call that function L of x equals f of a plus f prime of a times x minus a. We call that the linearization of f at a. You say, well, what's the difference? Well, there's no difference between the two, right? So linear approximation, the tan line approximation, the linearization of f at a, those are all exactly the same thing. They're all the equation of the tan line, right? So I'm not going to split hairs with you on the language there. If you're asked for the linear approximation or the linearization, you're really just finding the equation of the tan line. That's all it is. But what's required to do that, right, the same thing you would use to find the equation of a tan line. You have to have the coordinates of your point. So that's your a, f of a, what's the point in question. And then you have to have the slope of your tan line. Right? So that's your f prime at a, right, that particular a value. And then you're just plugging those values in. Okay? So it's no different than anything we've done before. We're just doing it with a little bit different notation. So for example, find the linearization L of x of the function f of x equals ln of x at the point where a equals 1. So as always with finding the equation of a tan line, finding the linearization, we need to find the derivative of our function so that we can find the slope of the tan line at that point, in this case where a equals 1. And then we also need to know the y coordinate of the point, right? Because our x coordinate is a, which is 1. So we find our derivative, f prime of x, the derivative of ln of x is 1 over x. So f prime of 1 would be 1 over 1, or 1, and then f of 1, if we plug 1 into our function, the natural log of 1 is 0. So if we were writing the equation of a tan line, I would be looking at the point 1, 0 with the slope of 1, right? That's the value of the derivative at that point. But here we're just going to plug it into the context of our linearization. So L of x is f of a plus f prime of a times x minus a. And so I'm plugging in f of a, which is 0, f of 1, f prime at 1, which we found to be 1, and then a is 1. And then we're just simplifying that. And I get L of x equals x minus 1. Now what is that? That is the linearization of our function f of x at the point where a equals 1, or at the point 1, 0. It's also the equation of the tan line at the point 1, 0. That's what it is. Okay? So it's just different notation, that's all. Let me give an example of how something like this can be used, right? When we talk about this linear approximation idea. You know, because ultimately what we're doing then is we're using the tan line to approximate the curve. You know, so instead of looking at the curve f of x, we look at the graph of the tangent line L of x, the linearization. And as long as we're relatively close to the point at which that tan line touches our curve, the tangent line is a pretty good approximation to the curve. Right? They resemble each other very closely. Now, of course, the further away you get from that point, then, right, there's a difference between the two, but as long as we're relatively close. So, for example, part A, let's find the linearization of the function g of x equals cube root of 1 plus x at the point where a equals 0. So here's our function. We're interested specifically at the point where a equals 0. So we want to find our linearization first of all. So let's find our derivative, g prime. Now that's cube root of 1 plus x, which is 1 plus x to the 1/3, right? So power rule, derivative would be 1/3 times 1/3, 1 plus x raised to the negative 2/3, decrease the exponent by 1. Now there is a chain rule here, the derivative of the base, 1 plus x, but that derivative is just 1. So I don't need to add that on there or tack that on. So the derivative g prime is 1/3, 1 plus x to the negative 2/3, or maybe if we want to clean that up, write it back in radical form, drop that to the denominator with the positive exponent, put it back in radical form. That would be the cube root of 1 plus x squared. But again, I don't necessarily have to do that. It's all about finding this. I need to know the value of that derivative at a equals 0, right? Or at x equals 0. So what form you put the derivative in is irrelevant as long as you can do the calculation. So we find our derivative. We have the value of the derivative at the point where a equals 0. So g prime of 0, if I plug 0 into that derivative, that would be 0 plus 1 is 1. The cube root of 1 is 1 times 3 is 3, so I get 1/3. We also need the y-coordinate of our point. All right, so when a equals 0 or x equals 0, g of 0, and I'm plugging that back into our function to get our y-coordinate, g of 0 would be the cube root of 1, which is 1. So again, that's all I'm doing is I'm finding the derivative, the value of the derivative, and the value of the function at the given a value. And then we're plugging it into our formula. So the g of x then can be approximated by g of a plus g prime of a times x minus a. So in this case, where a equals 0. Now again, this is an approximation for the function when x is near 0, because that's our a value. So I get g of x equals g of 0, which was 1, g prime of 0, we found that to be 1/3, and then x minus 0, or simply then 1 plus 1/3 x. So this is our linearization. We're saying two things here. We're saying that g of x, our function, can be approximated by this equation 1 plus 1/3 x as long as x is near 0, because that's our a value. We're also calling that the linearization. It's the equation of the tan line. That's what we found. L of x is 1 plus 1/3 x. That would be the equation of the tan line to that curve at the point 0, 1. Okay? So again, it can be confusing because you're calling it different things, but that's what it is. All right, so we could also say then if you just take your function g of x, which is the cube root of 1 plus x, so how about we say it this way? I'm telling you that I could approximate the cube root of 1 plus x, that's our function, by using this equation 1 plus 1/3 x as an approximation to the cube root of 1 plus x, but again, as long as x is near 0, okay? So in part B, that's what we're going to do. Let's use that approximation to approximate the cube root of 0.95, right? So the cube root of 0.95, that's our cube root of 1 plus x. I want to approximate this value. So if I look at the cube root of 1 plus x as the cube root of 0.95, so 1 plus x would be equal to 0.95, which makes x equal to negative 0.05. I just solved that equation for x. So now I could then say that the cube root of 0.95 could be approximated by that equation, 1 plus 1/3 x, or 1 plus 1/3 times the x we just found, negative 0.05. Now notice negative 0.05, we said that's as long as we're near 0, because this approximation is good as long as x is near 0, which negative 0.05 is pretty close to 0. So if I plug that into our approximation, I get approximately 0.9833. And then if you actually plug cube root of 0.95 into your calculator, you get approximately 0.9830. So this is our approximation that we get using our linear approximation 1 plus 1/3 x to approximate the cube root of 0.95 with x equal to negative 0.05. And notice if I just actually plug it into the calculator, I get something that's pretty close. I get 0.9830. It's not off by much. 3 tenths, 100,000, 3 10,000ths. That's the difference between the two. And of course the question always is, well, why do we need to bother with this when all I need to do is just plug it into the calculator? Well, you got to keep in mind the long game here. This is an approximation technique. This is a fairly simple little function. There's nothing tricky about that. I mean, I can easily plug that into my calculator. But you have to think of the broader application of stuff like this. If we're working with a function that's really, really complicated, really ugly, really difficult to manipulate, then if I can come up with a way to approximate that curve or that function using a much simpler equation or function, and you don't get any simpler than a linear function, So if I can approximate my curve with a line, as long as I'm relatively close to the point in question, then I can get a decent approximation to that curve. You know, and there's all different types of approximation techniques. I mean, this is just one, the linear approximation or linearization of a curve. You know, there's all kinds of different approximation techniques that are used in mathematics. You know, so when you're working with really, really ugly functions, or sometimes we can't even come up with the actual function, the best we can do is approximate the function, then it gives us something to work with, right? So you kind of have to keep that in mind. We are still working with very simple situations, but there's a lot of, you know, there's broader applications to this stuff. So part C, I just redid the same one. Instead of 0.95, let's approximate the cube root of 1.1. Right? So again, just to show you how this is working. So this is the number I'm approximating. And so again, we're using our function g of x, which was cube root of 1 plus x. And we're going to use that to approximate the cube root of 1.1. So 1 plus x then is 1.1. That's our radicand. So I'm using then x equal to 0.1, which again is pretty close to 0. Right? So we said as long as we're close to 0, then we can use that equation 1 plus 1/3 x to approximate our value. So the cube root of 1.1 then could be approximated by 1 plus 1/3 x, which is 0.1. And you get approximately 1.0333. Now again, if you were to plug that into your calculator, cube root of 1.1 into the calculator, you're going to get approximately 1.0322. Right. So again, it's pretty close, right? 1.0333, 1.0322. Pretty close to each other. Right? So a decent approximation. Okay. Now, just to show you by what we mean by we keep saying as long as we are close, as long as x is close to 0, right? Because we found the equation of the tan line at the point where a equals 0. So we need our x value to be relatively close to 0 in order to use this approximation. So what if I choose something that's a little bit further away? So how about we do the same thing with cube root of 2? And if you type cube root of 2 into your calculator, you're going to get approximately 1.2599. Okay. Now x in this case, and actually I have that incorrect, our x in this case would be 1, okay, because that would be 1 plus x, right? We're doing cube root of 1 plus x. So that would be cube root of 1 plus 1/3 times 1, right, using our approximation, which gives me approximately 1.33. So I did it with the wrong number when I did it, but I just realized that. So there's our approximation of 1.33. And notice we're getting a little bit further away from the actual value, whereas with the other two, we were within like decimal points, really like hundreds and thousands. This one, the actual value is 1.2599, and I get approximately 1.33. It's a repeating 3, right? It's 1 1/3. Which, I mean, still, it's relatively close, but you're getting further and further away, you know, from the actual value. And that's because 2, right, 1 itself, we're getting a little bit further away from 0 now. Right? I mean, yeah, 1 is pretty close to 0, but when you're talking approximations, yeah, that's a pretty decent amount to be off. Okay, so yeah, we'll talk about that a little bit more as we go into this differential stuff as well. You know, so there's kind of a, you know, a degree of accuracy that you want with this stuff. You know, it's like, okay, I can use it to approximate a value, but I have to be reasonably close to the approximation. You know, what's the amount that I'm willing to be off, in other words. Okay, so yeah, so we talk about differentials, we'll mention that. This last little statement that I have here, I have that a linear approximation can be used to give an approximation over an entire interval, right? So here we're just looking at, you know, kind of approximating at a specific point as long as we're reasonably close to that point. But what about an approximation over an entire interval? Like, how much is my function changing between 2 points? And can I come up with an approximation for how much the function value changes over an interval instead of just at a specific point? So that's actually what's going to lead us into this idea of the differential, or what the differential measures. Okay, Now again, there's nothing new here that we're going to talk about. We're just going to be a little more specific, or maybe a lot more specific, with the notation and the language when we talk about that derivative. You know, we keep talking about the derivative dy dx. Change in y over a change in x. So remember, where did dy dx come from? Dy dx came from the slope of the tan line, right? That was our whole derivative. It was the rate of change of the curve, but we were using the slope of the tan line to approximate the slope of the curve. So that's what this differential deal is going to talk about. So first, let y equal f of x as our basic function notation, where f is a differentiable function. Then we say that the differential dx, because when you have dy dx, there's change in y dy, there's change in x dx. We call dx a differential, we call dy a differential. So the differential dx, we consider it an independent variable, and by that we mean that we can make dx whatever we want it to be. You know, so when we talk about dy dx, what's the rate of change in our function? What's the change in y over change in x of our tan line? Well, we can pick the dx value that we want, you know, so we want to know how much the y value changes if we change the x value by a certain amount, okay? So how much does dy change if I pick a value for dx? So we can pick dx to be any real number. What's the change in x that we're interested in? And then how much does the function value change over that interval? Now dy, right, so that's dx. We just take that as an independent variable. Now dy, if you look at our simple equation for the derivative, right, f prime of x is dy dx. And then just solve that for dy. The differential dy then is given by dy equals f prime of x dx. Right? And that's just solving the equation f prime of x equals dy dx for dy. So in other words, dy, the change in y along our tan line, would be equal to the derivative of our function at the x value times the change in x. That's what that's telling us. Now look at this little graph that I have below that. This is critically important to understanding all this, what we're actually talking about and measuring here, right? So we have our curve y equals f of x, okay? Here's the actual curve itself. And we're interested in the tan line at that point P on our curve. So here's our point of interest. And then whenever we talked about the derivative, we were talking about the slope of the tan line, right? So we have our tan line to the curve at that point. And so dy dx, what does that measure? It measures the change in the y value along the tan line with respect to the change in x, okay? But again, we're talking about the tan line at a specific point, at that point P, whose x coordinate is whatever x is. All right, so I've got a bunch of things labeled here. So there's two things I'm going to talk about: the change in y with respect to the tan line, but also the change in y with respect to the actual curve. So you notice over here I've got this delta notation, that capital delta, the triangle delta y, and then our dy. So here's our dy, which is the change in y with respect to the tan line. So if we move along the tan line from point P to point R along the tan line, then the amount that the y value changes is dy between those 2 points. So my drawing is off just a tad. I want that to match up with the R value. Okay. So that's our dy. That's the change in y with respect to the tan line. Then you have delta y, which is the actual amount that the curve would change, the y value along the curve, y equal f of x, between the 2 points on the curve, P and Q. So as we move along this curve from P to Q, the y value changes by some amount. That's delta y. So dy and delta y are two different things, right? Dy is how much the tan line changes, or how much the y value changes along the tan line. Delta y is how much the value changes along the curve. Okay, so those are typically two different values. Look at the x though, right? So when I look at the actual curve at our point P, it has an x coordinate. And then we move some distance along the curve with respect to the x value. We could call that delta x with respect to our actual curve, so that the x coordinate of point Q would be x plus whatever delta x is. All right, the distance from here to here. But notice when we talk about the points on the tan line, the distance in the x coordinates of our 2 points P and R are still the same as the distance between the x coordinates of P and Q. Now with respect to the tan line, that's what we call dx, right? Dx is the change along the tan line of the x coordinates of those 2 points. Delta x is the change along the curve with respect to those 2 points. So P and Q when you talk about the actual curve, P and R when you talk about the tan line. But either way, delta x and dx, those are the same. All right, so how far we move along or with respect to the x-axis, whether we're on the curve or on the tan line, is the same. So delta x and dx are exactly the same value, but delta y and dy are different. Okay, because the change in the y value along the curve is different from the change in the y value along the tan line. But what we've been doing and what we ultimately do is we use this to approximate that. All right, so when we talk about that slope, right, dy dx is the slope of the tan line. Well, if we move away from our point in question and we're using the tan line to approximate the curve, then there's going to be a difference between dy and delta y, because the curve changes the y value, and the change in the y value along the tan line are two different things. Right? Now again, that may seem a little bit confusing or complicated when you first look at it, but the basic idea here is, look, the delta notation with the triangle, that's the notation when we're using that when we're actually talking about exact values. So with respect to the curve itself between 2 points on the curve, delta y is how much the curve changes, how much the y values change. When we use that d notation, the dy dx, that's what we use when we talk about the derivative. But the derivative refers to the tan line. And so that's the slope of our tan line, the rate of change in the tan line. Dy is the change between the y coordinates of the points on the tan line. All right. And because the tan line is not the same as the curve, then those y values are different. Dy and delta y are going to be different. But dx and delta x are the same, because horizontally you're moving the same distance either way. Okay? So it's kind of critical that you understand that notation as far as what we're measuring. Now what we're going to do with it is going to be still the same thing we've always done. We're going to find derivatives. But what I'm worried about, what I'm interested in here is when you talk about a differential, what does that differential actually measure? And the fact that we're using an approximation when we talk about dy as opposed to the actual value, which is delta y. So dy represents the change in the tan line. Right? Dy is the change in the tan line. How much that tan line rises or falls, right? How much the y value changes. Delta y represents how much the actual curve changes, right? So y equals f of x, the actual curve itself, how much does that rise or fall? As your x changes by some amount, which with respect to the curve is delta x, with respect to the tan line is dx, but those are the same, right? Because the horizontal distance is the same, either way. So then the slope of the tan line, which is the line passing through the points P and R, so I just labeled it that way, the slope of the tan line passing through the points PR, is given by f prime of x, right, which is dy dx. That's what our derivative is. It's the slope of the tan line. So then the distance from S to R in our diagram, that was the dy. Get rid of some of this mess out of my way. All right. So when we talk about the distance from S to R, right, so that vertical distance here, that's the change in the y coordinates of our tan line, right? So that's dy. And dy, we said from that equation earlier, can then be found by taking f prime of x times dx. And again, that's just coming from that equation, f prime of x equals dy dx. And we're solving it for dy, so that dy equals f prime of x dx. So now again, ultimately, what are we using this for? We're using dy to approximate delta y. And we know from our previous and earlier discussions on this that that approximation gets better the closer those points are to each other, or we'll say the smaller that delta x is, right? So back when we were doing all that secant line stuff and we were looking at the slope of the secant line, we said the slope of the secant line gets closer and closer to the slope of the tan line the closer these 2 points are to each other, right, on the curve. So that's the same idea. The approximation dy for delta y, it's a better and better approximation as delta x gets smaller, right? So if we shrink delta x, then dy is a better approximation of delta y. So that's going to go back to, like I said, kind of initially when I introduced this, we'll call it like margin of error. You know, so in other words, I can pick the delta x, I can pick the dx, right? How far away from the actual point do I want to be? Well, let's pick a delta x or a dx that's relatively small, you know. So we want to set the parameter as far as how close we want to be, how accurate we want to be. And then once I tell you how accurate I want to be, then I can actually tell you how much the y value is going to change. But I can use the tan line to approximate that value. Okay. So it's still all about approximations here. It's still all about using an approximation for the value instead of the actual value. But as long as I'm reasonably close, it's a good enough approximation. All right, this next example, again, this is a generic little example of how we can work with differentials. Now, typically, if you're asked to find the differential, it's implied that you are finding dy. Okay, unless otherwise stated, you know, sometimes they'll say find the differential dy, sometimes they'll say just find the differential. But it's understood that you're finding dy, unless otherwise stated. So when we say find the differential of the function, y equals x over 1 plus 2x, we're finding dy. But again, you're going to do it like you always did. You're going to find the derivative. All right, so you start by finding dy dx. You find the derivative of the function. And then you do whatever needs to be done to find that derivative. In this case, it's a quotient rule, right? It's low d high minus high d low over low squared. And then when you simplify, you actually can, I've got a plus 2x minus x, minus 2x, excuse me. And then there's a 1 up in the front of that. So I'm left, you simplify that, and I've got just 1 over 1 plus 2x squared. Now what is that? That is dy dx. That's our derivative, right? That's what I would use to get the slope of the tan line. But then if I want the differential dy, all I'm going to do is solve that equation for dy, and I get dy equals 1 over 1 plus 2x dx. Right? So all you're doing is you're just bringing the dx over to that side of the equation. That's all. That's the only difference between what we've done before and what we're doing here. Okay? So it doesn't change how you find the derivative. You just take that extra step, solve it for dy equals your derivative, f prime of x, times dx, and that's your differential. So similarly with the next one, right? So here I'm finding the differential dy. This time we're going to actually evaluate dy, given a value of x equal to pi over 3 and dx equal to 0.05. So we're looking at, in this case, the equation y equals cosine of x. We want to approximate dy, so again, we'll start by finding our derivative, dy dx. The derivative of cosine is negative sine. So then dy would be negative sine x times dx. That's our differential. And then we can approximate dy by plugging in the given values for x and dx. Right? So with x equal to pi over 3, dx equal to 0.05, I get dy approximately equal to negative 0.043. Now again, what is that measuring? I mean, that's a value for dy. What does that measure? What does that negative 0.043 tell you? Remember, what is dy? dy is an approximation to delta y. where delta y would be the change in the value of the function. If we started at x equals pi over 3 and we moved a distance of 0.05, this is telling me that the value of the function would change by approximately this amount. All right? Now I can calculate the actual change, which is delta y. This is giving me an approximation to the change, right? So in other words, if I start at the point where x equals pi over 3, calculate my function value. Right? So I just want to show you how this works. So if I start at pi over 3 and I find the value of y equals cosine pi over 3, which we all remember from trig, cosine of pi over 3 is a half. So there's our function value for pi over 3, at cosine of pi over 3. And then if we move a distance, dx, which is also delta x, of 0.05. So I look at the point where x equals pi over 3 plus 0.05. All right, so we move a distance of 0.05 away from pi over 3, and we look at the cosine value. You're going to get approximately 0.456 if you plug that into your calculator. So look at the difference in the y values. So this is the cosine value at pi over 3. And then if we move a distance of 0.05 from pi over 3, here's the function value at that point. And look at the difference between the two. So if I take 0.5 minus 0.456, I get a difference of 0.044. So what happened to our function value? It decreased by 0.044. Look at what our approximation told us. Our dy was negative 0.043, right? So it's telling us that the value should change. It should decrease by approximately 0.043. The actual change was 0.044. Pretty darn close. We're only off by 1,000th. All right? So again, it's kind of what I talked about earlier. It's using an approximation. Now in this case, obviously, I mean the approximation is a little bit more difficult than the original function. All right, because my function is cosine x, my derivative is negative cosine x. So there's not much difference between the two, and we're using one to approximate the other. But remember, this is illustration, right? As you work with much more complicated functions, this begins to make a little more sense in that if I can use a function to approximate another function, but I can do it with a simpler function, then I'm just saving myself a bunch of work. And as long as my approximation is reasonable, then that's good. It's good enough. All right, so here's an application. So there's applications in this section as well. Now, what I worry about with these is that we tend to want to confuse these with the problems that we looked at in the previous section with those related rates. But this is where, again, I'm going to harp on, when we're finding a derivative, what is changing with respect to the change in what, right? So what causes my quantity to change? When we did those related rates, that's the ones where we were changing with respect to time, right? Here, it's a little bit different. So you've got to be careful with, again, what is causing the change? What changes with respect to what? So when we find a derivative, all right, what am I differentiating with respect to? What's going to cause the change? So this is, again, coming out of the homework section, page 255, it's number 34. I've got the radius of a circular disc given as 24 centimeters. With a maximum error in measurement of 0.2 centimeters. Right? So we know what I call it the ideal measurement. So we want the ideal measurement of our radius to be 24 centimeters for our disc. But we're allowed an error of 0.2 centimeters in this case. So you kind of think of this when, like in a manufacturing process, and maybe this little circular disc is a component in some bigger or larger piece of machinery, right? So I have to put this onto something else. So this piece of this disc is maybe even manufactured at a completely different facility than the actual piece of machinery that we're going to build. So we manufacture these discs and then we ship them off to the main facility and then they assemble the product. So we have specifications. We know what the measurement of our disc has to be. We know the radius has to be 24 centimeters. We're given a tolerance level, we call it, right? There's a margin of error. There's a tolerance level of 0.2 centimeters. So as long as I'm within 0.2 centimeters of the actual measurement, then I have a disc that's usable in the construction of the item. And then, of course, if we're off by more than that, then the disc that I manufacture is not going to be usable, right? So yeah, so this gets done all the time in manufacturing, right? There's tolerance levels. Not everything is going to be measured perfectly, right? So you have to make sure that whatever it is you're constructing meets tolerance levels. So you're within the margin of error for whatever error we're allowed. Now, so that kind of gives you a little bit of background of how something like this is used. All right, so our ideal radius is 24 centimeters. We are allowed a maximum error in the radius of 0.2 centimeters. So our question is, let's use differentials to estimate the maximum error in the calculated area of the disk. All right, so if we're off in the measurement of our radius, how much is that going to affect the area of the disk? Right, now again, notice there's a difference here between these and the ones we looked at in the previous section, where in that case, the area might change over time, right? So we were looking for change in area, which we're doing here. How much error is in the area? So that would be a dA. But it's not changing over time. It's changing with respect to the measure of the radius, right? So when I look at the change in the area here, it's not dA dt. It's not changing over time. It's dA dr because the change in the area occurs based upon the change in the measure of the radius. That's the biggest sticking point with these application problems, and it's what I find to be probably the biggest issue with all of this, with these applications. It's just not being clear or paying attention to what is changing with respect to what. So is it a change over time, as we had previously, or is it a change with respect to some other quantity, which is, in this case, the radius? So that's what you've got to pay attention to. So if we're looking to calculate the error in the area, then we're looking for dA, right? How much the area changes. So of course I'm going to start with the area formula for a circular disk. For a circle, area is pi r squared. So then we want the change in the area, dA, but again, where it's a change with respect to the radius. So it's not dA dt here, it's a straightforward differentiation of the area with respect to its radius. So I'm differentiating with respect to r. I've got dA dr. Now that makes the change in r 1, right? So ddr of r is 1, just ddx of x. So over on the right side, we're using our power rule, pi r squared. The derivative, again, remember pi is a constant, so it's just power rule, 2 pi r, times dr, right? This change in radius with respect to radius, which is 1. And that's kind of interesting to see, too, as you recognize 2 pi r, that's the formula for what? Circumference of a circle? So it turns out that the derivative of the area of a circle is the circumference of the circle. Right, but again, this is done with respect to r. So then our differential dA, which is what we're asked to find, what's the change in the area, the error in the area, dA then would be would be 2 pi r times dr. Just solving that equation. So again, remember, dA is an approximation for delta A. Delta A is the amount of error in the area, and we're using dA to approximate delta A. Okay. Again, we're calculating the area, the error in the area. Say that 3 times fast. So then with r equal to 24, that was our ideal radius, and dr equal to 0.2, that was the amount of error that we were allowed in the measurement of the radius. Right? So there's our r and dr. So again, we're just plugging that into dA. So dA was 2 pi r dr, so 2 pi r dr, which gives us approximately 30.1593, or say about 30.2 square centimeters. Now what is that? That is dA. That is an approximation to the error in the area of our disk. Now you can calculate the actual change in the area. You can calculate delta A. If you calculate the area with the ideal radius of 24, and you calculate the error, Let's say it again 3 times fast. You calculate the area taking into account the error of 0.2 centimeters. So if I calculated with a radius of 24.2, and you take the difference between those two, you're going to get an actual error in the area of 30.285. Which again, though, notice it's pretty close, right, to that 30.1593 or approximately 30.2 that we got. Right. But again, this is all we're interested in. And you can use delta A if you want to do that calculation, just to kind of double check yourself. That should be reasonably close to the value that you found. All right. Right, but again, I mean, all you're doing here is very similar to the applications before, right? We're finding a rate of change, but what is it a rate of change with respect to, right? So what is changing? Is it change over time? Or in this case, is it change with respect to a measurement in the radius? So that's really what you have to be careful of. And I know that's tricky. I know that's what throws people off with these. All right, so that's the value that we're interested in. That's our approximation. Then we have a couple of other measurements that we can make use of. We can calculate what's called the relative error. What is the relative error? And what is the percentage error? So first, the relative error. The relative error is defined as the ratio in the error in the measurement to the actual measurement. So in this case, it's delta A divided by A, or we're using dA to approximate delta A, so dA divided by A. Now you can do this one of two ways. You can use the formulas themselves, because this is the formula we found for dA, right? dA was 2 pi r dr. And then we also have the formula for area, which is pi r squared, and so you can set up the formulas. And if you simplify that, you can divide out the pi, you can divide out one of the r's, you end up with 2 dr over r. And then we can plug in dr, we can plug in r as given in the problem, and we come up with a relative error of 0.016 repeating, or say approximately 0.017. All right, so that's just using the formulas. It's dA over A. So I take the formula for dA, divide by the formula for A, simplify, plug in my values. Now, the other way you could do this, should you choose, is to do this. Right? We found delta A above, right? And we find delta A like this. And we take the difference between the actual area and the area given the error in the radius. And so you can calculate delta A. You can also calculate A. I mean, this is what A is right here. And then you divide the two. And you should get a value that's relatively close to the one that we got. Okay. I like doing this because it does, I don't have to bother with all those calculations above. I simply use the formulas that I already found and then just plug our values in. But if you want to do it the other way, you're welcome to do it. Now, the relative error, I don't find that very useful. I mean, so what? Relative error of 0.017. What does that tell me? I don't know. But then there's this percent error, which is probably a little more useful. If you take the relative error and you multiply that by 100%, so here's our relative error of 0.017 times 100%, move the decimal twice, I get 1.7%. That's a little more meaningful. That gives me a percentage error in the actual measurement, in this case of the area. So it tells me that if the radius is off by as much as 0.2 centimeters, then the measurement of the area of the disk could be off by as much as 1.7%. That's a little more useful measurement to me anyway. Okay. But yeah, I mean, these applications, like I said, they can be a little bit tricky because, again, it's all about forcing, you have to focus, is what I'm trying to say, on what actually is being measured and what causes that measurement to change. Okay? Is it change over time with the related rates where we're doing a DDT? Or is it change with respect to some other specific quantity, like in this case, the radius, so we did DDR. And then this relative error and percent error, I'll also ask you for that. And that's it for this section.